In this video, we're going to do some tricky arc length examples. If we have a function f, then the length of f of x from x equals a to x equals b is the integral from a to b of the square root of 1 plus f prime of x all squared dx. If f is continuous and differentiable on the interval a to b. But what if not? For example, if f has a cusp or vertical tangent at some number between a and b, then this integral is undefined because the derivative is not defined there. For example, in this curve, we see that at c1, there is a cusp or sharp corner. The derivative is undefined at a cusp. Same at c3. So this formula is going to have a problem at those x values. And even here at c2, there is a vertical tangent, and that turns out to be an even bigger problem, as we will see. Now you might say, well, let's just take the arc length in pieces. Let's integrate from a to c1, from c1 to c3, and from c3 to b. And in fact, that's exactly what we're going to do. You can see that this curve is perfectly continuous from a to b. It just has these cusps at c1 and c3. A bigger problem is going to be at c2 and at a, where we have vertical tangents. The slope of a vertical line is undefined. So if we have a vertical tangent, the derivative represents the slope of the tangent line. So when the tangent line is vertical, the derivative is undefined there. So this formula is a problem there. Similarly at a here, we can see that this tangent line goes vertical right there at a. So the derivative is undefined there too. So what to do? Well, as we mentioned, if f is continuous and differentiable except for a cusp at some number in between a and b, we'll just take the integral piecewise, add the lengths on each differentiable interval to get the total arc length. The length from a to b is the length from a to c plus the length from c to b. So just integrate separately. Here's a quick example. F is a function that is continuous from a to b and is differentiable except at c1 and at c2, where we have cusps. So provided we have a formula for f of x, the length from a to b is the length from a to c1 plus the length from c1 to c2 plus the length from c2 to b. So we can just set up three separate integrals and evaluate those integrals separately. So what about those vertical tangents? So now suppose f is a continuous and differentiable function except for a vertical tangent at some c. If c is one of the endpoints, what we'll do is we'll try to rewrite the curve as a function of y and set up an integral for the length in terms of y. This will work assuming that we have no other issues between a and b, because if there's a vertical tangent when the function is written in terms of x, that will become a zero slope in terms of y. And if c is in between a and b, then we can split up the interval from a to b as we did before, and then c will be at one of the endpoints, and we can follow this first procedure. Let's do an example. Set up a valid integral for the length of f on the interval from 0 to 2, where f of x equals the square root of 8x. Now, if you know what the graph of f of x looks like, you will be suspicious right away that we're going to have a problem at x equals 0. Here is f of x equals the square root of 8x. And here's x equals 2, here's x equals 0, where we have what looks like a vertical tangent. We can confirm that by taking the derivative of f and seeing that it is undefined at x equals 0. So sure enough, the arc length integral from 0 to 2 of the square root of 1 plus f prime of x all squared dx is undefined because f prime of x is undefined at x equals 0. So here's our solution. Let's rewrite the equation y equals the square root of 8x as a function of y, where y is the independent variable and x is the dependent variable. Solving for x, we've got y squared equals 8x, so x equals 1/8 y squared. This equation represents the same graph, but because we've now written it as a function of y, we need to integrate over the y values, not the x values. We can just plug in 0 and 2 into the original function to get f of 0 equals 0 and f of 2 equals 4. So we know we're going to be integrating from y equals 0 to y equals 4. Notice that g of y equals 1/8 y squared is continuous and differentiable on that interval from 0 to 4. And since it represents the same curve, it will have the same length. So to use the formula, we need to take the derivative of g of y. Then 1 plus the derivative of g of y all squared is 1 plus y squared over 16. So the length is the integral from 0 to 4 of the square root of the quantity 1 plus y squared over 16 dy. This is a valid integral that represents the length of the curve. Returning to this first example, we do have to be a little bit careful. For example, if we have a vertical tangent at an endpoint, we might think, let's just take the function f on the interval from a to c1 and rewrite that in terms of y. The trouble there is that at this point, we have a horizontal tangent. And so if we were to rewrite this curve in terms of y, at any point where the slope is 0 in terms of x, when we rewrite it in terms of y, it will become a place of undefined slope. In that case, we can take a smaller piece of the curve and rewrite that. For instance, just to zoom in, we could take just this little piece stopping short of our horizontal tangent here. Maybe we can call this D. This little piece from A to D we could rewrite. Just zooming in, we can set up an integral for the length of this part of the graph by rewriting f as x equals g of y and then integrating from, in this case, f of d to f of a, since f of d is the smaller y value. This integral will give us the length of the curve from x equals a to x equals d, between d and c1, and from c3 to b. We can integrate in terms of x to get the lengths of these pieces of the graph, because we have no places in this interval where we have any vertical tangents. Whereas from A to D, from C1 to C2, and from C2 to C3, these pieces of the graph have vertical tangents at one end, and therefore we would need to use the rewritten equation in terms of y in order to integrate to get these lengths. Once we have all of our integrals set up, we just add them up to get the total length of the curve from A to B. In summary, if f is continuous and differentiable on an interval from A to B, Then the length of f of x from x equals a to x equals b is the definite integral from a to b of the square root of the quantity 1 plus f prime of x all squared dx. If f has a cusp, or vertical tangent, at a number c between a and b, split up the curve into pieces. If f has a vertical tangent at an endpoint of an interval, rewrite the curve as x equals g of y, and set up an integral for the length in terms of y. Check to make sure g is differentiable on the corresponding y interval c to d, where c equals f of a and d equals f of b. If it isn't, you may have to split up the interval further. I hope you found this video helpful.